Welcome once again to everyone to this new webinar. Today's webinar will be about a new constitutive model, the ASDSteel1D. The presenter will be Alessia Casalucci, and she already presented this model in the latest CompDyn 2025 in Rhodes. And now we just created a pull request in OpenSees, so this new code will be in the official OpenSees repository soon. So just before Alessia starts, I will give you, I will just share my screen just a second to show you where is the code if you are interested. Let me share my screen. Okay, so if you go, now if you look for the source code, it is available. But if you try to use the official OpenSees version now, of course, you will not be able to use this constitutive model because we did a pull request just yesterday. So if you know how GitHub works, you can go in OpenSees, you go in pull requests, and you will see that yesterday we did this new pull request. So it will take a few days for the maintainers to review the code and accept it. And here there is also a link to the documentation here. And if you know it works, you can see the code, you can see the changes. Otherwise, you have to wait for the official OpenSees version to be compiled again. Otherwise, on Monday, we will release the new STKO version 4.1. And always on Monday, Professor Tarke will release its own unofficial version of OpenSees that will contain this constitutive model. So if you want to start using it, on Monday, you will have the newest OpenSees version, unofficial version, the new STKO version, and the recordings for this webinar and the files that Alessia will share with us today. Okay, so I stop sharing my screen. So remember, just everything will be ready on Monday with the new version of STKO. So I stop sharing. And Alessia, you can go ahead.
Okay, thank you, Massimo, and good afternoon, everyone.
I think there is also, just before you start, there is already a question. I don't know if it's related to what I said. What operating system do you recommend to make OpenSees development? It's up to you. We use both Windows and Linux, so it's really up to you. You can, if you know how to compile it, whatever operating system is fine. If you don't know how to compile it, maybe in Windows you will find more precompiled releases. But it's up to you. There should be no problem in compiling in different operating system. Actually, for example, if you look at in the here in the OpenSees GitHub, they have workflows for both Windows, Ubuntu, and they also have Mac, I think. So there should be no difference. Okay, so Alessia, go ahead. Thank you.
Okay, thank you, Massimo, and good afternoon. Good afternoon, everyone. Let me share my screen. Okay. Okay. Well, as Massimo said, I will give you firstly a short overview of the new uniaxial material, the ASDSteel1D, and briefly explain some theoretical aspects. Then I'll dedicate a few minutes to material testing phase that will help you understanding the meaning of each parameter. And you'll see that it's actually much easier to use than STEEL02 or other existing STEEL models in OpenSees, thanks to its reduced and more intuitive parameter set. Let's say it's a more optimized solution. After that, we run a numerical application based on an experimental test from peer report of 2007-11, which investigate bar buckling in reinforcing a concrete bridge column. This will help us validate the model's behavior under cyclic loading conditions. Well, so let's start with a brief overview of the ASDSteel1D model. This is an uniaxial material model specifically developed for reinforcing steel bars. It was designed to reproduce the most relevant physical mechanism involved in the cyclic behavior of the rebar, like cyclic plasticity, damage, buckling, and bond slip mechanism. In addition, the model implements the implex integration scheme, improving both performance and numerical stability. And to avoid mesh independence issues, we also included a regularization strategy based on a multiscale homogenization principle. As you can see in the blue box, only 4 parameters are mandatory. In particular, we have Young modulus, the yield stress, the ultimate stress, and the ultimate strain. Well, then if you decide to activate additional mechanism, for example, buckling, it requires just 2 more parameters. For fracture, you need to set only 1 extra input, and for the slip requires 2 additional parameters. It's worth noting that the radius parameter appears in buckling, fracture, and slip. So it's shared across the modulus and does not need to be redefined. Compared to other steel model in OpenSees like STEEL02 or the ASDSteel1D, this model is more physically complete but also more compact. So let me give you a very quick, simple overview of the theory behind the model, starting from plasticity. Well, the plastic behavior in ASDSteel1D is based on a 2-term Chabosh kinematic hardening model. This model is well suited for simulating cyclic loading condition and particularly effective in capturing ratcheting behavior where the material exhibits progressive accumulation of plastic strain under asymmetric cyclic loads. As I said before, we also included the fracture, which is specifically designed to reproduce the tensile rupture of steel bars. And the model introduced a scalar damage variable, D, which progressively reduces the effective stress. The damage activation is governed by the equivalent plastic strain. Once it exceeds a threshold value, the material enters in a softening regime, where the stress decays exponentially, as you can see here, and is a function of the accumulated plastic strain. This enables the material to simulate bar rupture under tension. Okay. Another important mechanism is the bond slip interaction between the rebar and the surrounding concrete. In our model, the user can choose any external uniaxial material to define the bond slip law, usually as a tau slip curve. And internally, the ASDSteel1D transforms automatically this into a stress strain curve and connects the steel and the bond slip materials in series. This ensures the stress continuity and strain compatibility. Now let's move on to buckling, which is one of the most complex parts of the model. Instead of using empirical formulas, we use a multi-scale inspired approach. We simulate a small portion of the bar called the representative volume element that includes the local effect like compression, deformation, and so on. To simplify the simulation, but also to reduce computational costs, we only model half of the bar, taking advantage of the symmetry. We divide the bar into 3 beam elements, and we represent the cross-section with just 3 fibers. We use a corotational formulation to simulate large displacement and rotation correctly. And finally, we could say that the central element lies at the inflection point of the buckle shape, where the bending moment is 0. And so we model it with a special rule to avoid the numerical issues. Finally, we implemented an implex integration scheme that is an hybrid algorithm that combines an explicit prediction step and an implicit correction step. This scheme is especially useful when dealing with highly nonlinear behavior, such as softening, slip, or large strains. It improves both stability and convergence, especially in cyclic simulation. As also Massimo said, in next days, you will find also the full documentation. I show you how it will appear to you. It includes brief description of the model, then the full OpenSees command syntax, a list of all the parameters and their meaning, and then you can find a bit of the underlying theory. And if you go down, you can find the notes in which there are the available response type, and finally a set of examples. For each example, you will find a Python script that you can download, and this script run a complete simulation in OpenSees Pi and produce the results that you can see also here. So now we can move on and I can talk about how to test and define the material parameters. Let me open STKO. Yes, I think it's that. And as you can see here, there is no geometry involved. We are just focusing on defining the material itself so that I can walk you through the parameter setup. And so when you create a new ASD model, this is what you'll typically see. First, you define the elasticity section. Here you can input the Young modulus. Then in this section, you can set the yield stress, the ultimate stress, and also the ultimate strain, which control the plastic and failure behavior of the steel. It is important to note that the stress values, both the yield and the ultimate, can be given in any consistent unit you want, such as megapascal, pascal, or even psi. The key point is that all the parameters must be in current unit. So, for example, if you give the stress in megapascal, also the Young modulus should be in megapascal, and similarly for geometrical quantities, so such as bar length or diameters, should be expressed in that case in millimeters or in meters if you're using Pascal. In this example, we are looking now, all the parameters are set in megapascal for stresses, and in millimeters we can see later for the length and radius. So now let's test and show you how it looks like. For example, I'm running a monotonic test, and I've set the target strain as to 0.06, so positive, and which correspond to the ultimate strain that I have defined in the material parameter. As you can see from the stress strain plot below, the material response starts off linearly, following the elastic behavior up to the yield. After yielding at a value of 400 megapascal, we enter to the plastic regime, and where the material continues to deform, but with reduced stiffness. And eventually, the curves flattens out as it approaches the ultimate stress of 520 and the ultimate strain of 0.06. So this is the shape intention. Now let's switch to compression. So I change the target strain from positive to negative, and we use the same parameter, material parameter. As you can see in the plot, the shape is perfectly symmetric with respect to the region, because we haven't yet activated any asymmetric inducing mechanism like buckling or damage. This default behavior is what you'd expect for idealized bar with the same properties in tension and compression that gives us a clean baseline. But of course, real bars behave very differently once you start to add mechanisms that actually govern their failure, for example. So let's take the next step and switch those mechanisms on one at a time, so you can see how the curve evolves. So first, I'll pick the fracture box. Doing that, yes, you could see here, make sure you have set the correct rebar radius, because the fracture model uses it for computations. In this case, we have set a radius of 6 millimeters. Now, watch what happened. After the ultimate strain, so sorry, yeah, monotonics, sorry. I set the target strain as 0.1. So after, as soon the strain exceeds the ultimate strain, so 0.06, the curve drops sharply, and that sudden loss of strength represents the steel bar cracking and losing its load carrying capacity. Next, let's activate buckling. So we untick the fracture and we take buckling instead. In this case, it's not enough to provide just the radius. You also need to specify the buckling length. You'll notice that the target strain, now we have to set it to negative because we are simulating in compression. The response curve, you could see, changed significantly. After yielding, the stress no longer increases linearly or plateau. Instead, it drops progressively, and this reflects the loss of actual stiffness due to buckling, which becomes more pronounced as the strain increases. Now let's move to the final mechanism, that is the bond slip. As I mentioned earlier, this is essential when simulating the interface between the steel bar and the surrounding concrete. Just like with fracture and buckling, in this case, it's also necessary to provide the radius of the bar, since it determines the effective bond area and does affect the slips to stress conversion. And then you have to link an external uniaxial material that represents the slip law. In STKO, for instance, there is a dedicated material called ASD bond slip. I show you, which simplify this process. It simulates this mechanism by placing 3 concrete materials in parallel, effectively reproducing the typical slip curve, as you can see here. So I link this material here, and as a result, I change the target strain. As a result, the overall stress strain response is now modified. After reaching a peak, you can see it drops and then stabilized at a residual value, showing the gradual loss of load transfer due to interface degradation. Now that we have test fracture, buckling, and bond slip, let's take a moment to talk about autoregularization. So you might have noticed that this option is automatically enabled. However, this is not at all mandatory. The user has full control over whether or not to apply regularization. If you decide to keep the checkbox ticked, the material response will be automatically regularized. Now, we want to go into the internal details of how the regularization is implemented for each physical mechanism, and so for fracture, buckling, and bond slip, because each of them has its own formulation. What is important here is that by keeping the option enabled, the material model in OpenSees automatically handles the regularization. But again, it's completely up to you. If you don't want any regularization and prefer a purely local response, you can simply uncheck the box. Then, if you have other stuff, well, you have the integration scheme. It can be implicit or implex. You already may know the difference between them. And below that, you have a few additional parameters. These are part of the advanced settings, and they are all optional. Most of the time, the default values are already work well. I tick the box only to show you. And we have the K alpha that defines the weight between the consistent elastoplastic tangent and the purely elastic modulus. A value of 1 gives you the full consistent tangent, while 0 uses only the elastic modulus. Then we have the max iter, that is the maximum number of iteration allowed in the Newton-Raphson loop, used by the representative volume element. And the default value is 100, which is usually sufficient for convergence in most situations. And two final parameters are the tol u, which is the tolerance on the displacement increment, and the tol r, which is the tolerance on the residual force. Both are convergence criteria, and they are their default values are 10 to the power of -6, which quite strict, but necessary for accurate simulation. So unless you are dealing with particularly difficult cases or numerical issues, you usually don't need to change this. So now that we have explored the ASDSteel1D material and tested its key feature, we can move on more practical application. Okay. So replicating a real experimental test. This part of the webinar is based on the study of Brown, Lemon, and Stanton, which want to capture the bar buckling in reinforcing concrete bridge column, and you can find it in peer report of 2007-11. In this slide, you're seeing summarize the main aspect we need to define to build our simulation model. We'll follow this key step one by one. In this example, we aim to simulate an experimental test in which a reinforced concrete column is subjected to an axial load and an increasing cycle lateral displacement. To replicate this behavior in STKO, we start by defining the geometry of the column based on dimensions reported in the experimental setup. Next, we assign the material properties, concrete for the cover and the core, and ASDSteel1D for the reinforcing bars. And we then move on to element selection. In this case, the column is modeled as a line element to which we assign a fiber section. Once the geometry and the...
Alessia, I think you're sharing the PowerPoint, not the entire screen.
Yeah.
Ah, it's fine. Okay, sorry. I thought you were showing the model.
No, next we'll share the STKO after that. Once the geometry and the material are defined, we apply the boundary condition and the loading protocol. Finally, we configure the analysis setting, specifying time increments, solver algorithm, tolerance, and convergence criteria. So now I show you the model in STKO. Well, to begin, we define the geometry of the column using two line elements. Could you see the STKO? Okay, perfect. Thank you. This choice is, so we use two line element. This choice is based on the experimental setup, where the total column height is approximately 1,719 millimeters, and the horizontal cyclic load is applied at 1,524 millimeters from the base. So by dividing the column into two lines, we ensure that there is an intermediate node exactly at the loading point, which will be useful for applying the lateral displacement. These lines are then joined, as you can see here, using a wire to define the continuous geometry of the column. Now let's define the physical properties of the section. From the experimental setup, we know that the column has a circular cross-section with a radius of 500 almost millimeters, 10 reinforcing bars, each with a diameter of 20 millimeters, that are placed symmetrically at a radius of 418 millimeters, and a continuous spiral stirrup that provides the confinement. This led us to divide the concrete into two zones: the outer part, which is the unconfined concrete, and the core, which is the confined concrete, due to the lateral pressure exerted by the spiral. So in STKO, we use a fiber section. And in particular, the section includes the two concrete zones. So the violet one represents the unconfined concrete, while the green zone is filled with confined concrete, and 10 steel fibers for the rebars positioned at the correct radius. In addition, since we are assigning this fiber section to a line element, we need to define a torsional rigidity that has been estimated from physical and geometrical data from the test. Then let's now look at the concrete material. For both unconfined and confined concrete, we use the ASDSteel1D. For the unconfined concrete that is used for the outer region, the key material parameters, and so the compressive strength and also the Young modulus are taken directly from the peer documentation, while the remaining parameters are computed following a special empirical relationship. In particular, the tensile strength is assumed to be 1/10 of the compressive strength. The fracture energy in tension is calculated using the empirical formula in which we have the compressive strength to the power of 0.18 times 0.073, and the fracture energy in compression is then set as 250 times the tensile fracture energy. These relationships are commonly used in literature to calibrate concrete softening behavior when direct experimental values are not available. Then, for a confined concrete, we use the ASD concrete 1D model with 9-point formulation. This model allows us to represent linear behavior under both compression and tension, including softening and fracture, to determine the peak compressive strength and the respective strain. We apply the Mander formula, which relates the confined and the unconfined compressive strength through the lateral confining pressure generated by the spiral stirrups. This calculation helps to ensure that the behavior of the inner core is realistically represented. And next, we define the material for the steel rebars using the ASDSteel1D model. All the mechanical properties, and so the yield strength, ultimate strain, and also the Young modulus are taken from the experimental report. And additionally, we activate one key feature, and so the buckling, by assigning a radius of 10 millimeters and an effective buckling length derived from the test data. Finally, we wrap everything together by creating beam section properties, where we assign the fiber section here and set the number of integration point to 5. And we assign it, as you can see here, to the entire geometry. We then define the element properties for the column. In this case, we use the displacement beam column, which is particularly suited for nonlinear analysis. In this property editor, we set the dimension to 3D, and the transformation type is set to linear. And we also assign it to the entire geometry. This completes the definition of the physical and element property that will be assigned to the beam column element representing the concrete column. Now let's move on to the boundary condition and loading definition. So first, we applied a fully fixed constraint at the base of the column. This is done by constraining all degree of freedom, translation in X, Y, and Z, as well as rotation around the X, Y, and Z axis. This replicates the experimental setup where the column is firmly anchored to the ground to prevent any movement or rotation at its base. Second, we applied a constant vertical load at the top of the column to simulate the effect of the permanent wave axial load. This vertical load is directed along the negative Z axis with a magnitude calculated based on the axial stress applied in the experiment. And finally, to simulate the cyclic lateral loading, we prescribed an horizontal displacement as the control load here, that is located at a height of 1015 millimeters almost from the base. The displacement is imposed in the global y direction with a unit amplitude of 1. And this unit amplitude is then scaled over time using a path time series. This path replicates the displacement history applied in this experimental test and has been regularized. Now that all the boundary condition and loading definition are in place, let's take a look at the analysis step used to simulate the response of the column. Well, we begin by setting up the recorder to extract key output quantities during the simulation. In particular, we decided to record the nodal displacement, rotation, reaction force, and moment, essential to evaluate the global response of the structure. Additionally, at the fiber level, we record the strain, stress, and as you can see here, the buckling indicator. This custom output provides deep insight into the local material behavior within the fiber section. After that, we define the constraint pattern. As can be seen, we apply a single point constraint, which fully fixes the base node. Then we define the vertical load, which simulates the sustained axial force acting on the top of the column. In this first analysis step phase, the time series is linear, meaning the vertical load is applied gradually, but then remains unchanged throughout the analysis. And after that, we define a standard static analysis. Anything special here? All the setup for static analysis. The load, we have a load control integrator with a duration of 1 because it should match the total duration of 10 series. However, we have enabled also the adaptive time stepping, which allows the code to automatically adjust the increment size. And we also use the pseudo time and load const to make sure that load remains constant during the steps and is not affecting by internal time increments. And finally, the wipe analysis. Then we could move to pushover test. We set a monitor to check the reaction moment at the base node, and then we define the horizontal load with the path time series. And finally, the analysis that is set almost as the previous, it's a load control analysis with the adaptive time step. So now if you run this model, we will obtain the result that I'm showing you. So I launched the monitor. I don't want to waste time, so I already ran the analysis, and it took almost 3 minutes to run the entire analysis of 10,000 time step. And in this plot, you can see the moment displacement that corresponds to the lateral movement in Y responds at the base node of the column. For comparison, I show you here, maybe it's better if I reduce this one, okay. Here on the right side, you can see the experimental moment drift of the specimen CT5 from the Peer 2007-11 report. Please note that experimental curve appear mirrored with respect to the simulated one, but this is irrelevant from a physical standpoint, as it is simply depends on the orientation of the y-axis in the coordinate system. Also, keep in mind that the units are different between the numerical simulation and the experimental data. In simulation, the moment is expressed in Newton millimeters and the displacement in millimeters, while in the experimental plot, moment is in kip inches and the displacement is in inches. To give a raw comparison, 1 kip inch is almost 113 Newton millimeters, and 1 inch is almost 25 millimeters. So for example, experimental moment of 4,000 kip inches corresponds to approximately 4 times 10 to the power 8 Newton millimeter, which is on the same order of magnitude as our peak simulated reaction moment. Similarly, an 8% drift on a column with a height of 1,500 millimeter correspond to a displacement of about 130 millimeter, which matches quite well with the maximum displacement in our simulation. So, however, I want to emphasize that I'm not aiming to have an exact curve match. My goal is to reproduce the global behavior and within a consistent magnitude. In the experimental test, in fact, additional phenomena like spiral fracture, Bauschinger effects had a significant influence on the response, especially in the post-peak range, that are not fully captured by our current model. So despite this significant this simplification, the numerical results show a reasonably good agreement, and we can observe clearly the degradation in peak strength and stiffness with increasing drift cycle. These trends are consistent with the experimental behavior. So now I can go in the post-process here, yeah. And I'm going to show you the dynamic response of the column throughout the entire loading protocol. Here you can see the lateral displacement developing under cyclic loading. The deformation is amplified by a factor of 5 to better visualize the global response. And as the cycle, show you the animation. So as the cycle progresses, the top of the column undergoes increasing lateral drift, while the base remains fixed, and this visualization highlights the accumulation of displacement and gives a clear picture of the overall deformation shape. Then I show you a sequence of fiber level results for different internal quantities. First buckling indicator, and then stress and strain. So I already have it, but you only have to select the beam shell fiber color map. So, and here you have the buckling indicator. So the buckling indicator represent here, okay, represent the lateral displacement of the steel bars, and I displayed it by selecting only the steel material because the concrete has not the buckling indicator as a response. And to improve the visualization, I also increase the particle size scale factor to 8 and making the individual fiber more visible. And additionally, here, the deformation scale is set to 5 to enhance the perception of curvature and buckling effect. Well, this animation illustrates how bar buckling initiates and progressively intensifies during the loading cycles. Lateral displacement are most pronounced in the compressive region near to the column base, where plastic deformation accumulates. Overall, this fiber level visualization allows us to monitor the evolution of the local buckling phenomena and to link them with the global deformation demand. Then I now present a sequence of strain visualization at the fiber level, shown progressively by filtering the material involved in the section. In the first plot here, all the material are included. So unconfined concrete, the confined core concrete, and also the longitudinal reinforcement. And this provides a comprehensive view of the overall strain distribution in the section during the entire loading history. And you can observe how strains start to accumulate progressively with increasing lateral drift. Initially, the outer concrete experience moderate tension and compression, but loading cycles intensify, both steel and core concrete develop significant plastic deformation. This global view is useful to understand the interaction between materials and how strain localized in different regions of the section. Then I hide the unconfined concrete, allowing us to better isolate and visualize the response of a confined core and the steel. So you can now see more clearly how the confined core concrete helps in limiting strain concentration in the early cycle. And then, however, as the number of cycles increase, the strain in the confined region begins to localize, especially near the base, indicating the formation of a plastic hinge. Finally, I show you the strain distribution only in the steel fiber. And this clearly reveals the development of plastic hinge and the progressive accumulation of inelastic strain in the longitudinal reinforcement, especially near to the base, where bar yielding and cyclic degradation are most concentrated. By filtering materials in this way, we can better interpret the contribution of each component to the section overall behavior. Now I pass to analyze the stress distribution at fiber level. So filtered by also, in this case, material types to progressively highlight the contribution of each component to the section behavior during cyclic loading. And first, all the materials okay. So firstly, all the materials are included, so unconfined concrete and steel. The stress distribution okay. The stress distribution evolves during the cycle with alternating compressive and tensile stresses depending on the curvature. And you can clearly see how concrete and steel share the loads in early stage and how stress progressively concentrate in the core and the reinforcement. In fact, if I are in the unconfined concrete, here you could I think, okay, I'm checked. Okay, we could focus on the confined core and longitudinal reinforcement, and the stress in confined concrete remains stable for the initial cycles, and as the inelastic demanding grows, stress redistribution becomes evident. I'll show you again, especially in the central core and in the bars, with a large tensile stresses on one side and compressive stress on the opposite side. Finally, I isolate the steel. Okay, to visualize the internal forces in the longitudinal reinforcement, the stress levels reach their peak values near the base, where yielding initiates to and gradually extend through the repeated cycles. And you can observe the alternating tension and compression in the bar, as well as residual accumulating due to cyclic plasticity. This detailed stress map confirmed the accuracy of the implemented steel material model in reproducing cyclic hardening and degradation. To better understand the local steel behavior under cyclic loading, I selected two specific steel fiber located at the extreme edges of the section. Particularly, I selected this one and this one on the other side. And these fibers are positioned symmetrically with respect to the section centroid and are representative of the maximum tensile and compressive demand at the base of the column where the plastic hinge developed. Here you can see the stress strain plot, okay, for each fiber. And this plot, these are plotted over the entire loading history. Fiber 9, initially the red curve, initially in tension, undergoes yielding and strain hardening, followed by unloading and reloading into compression. The loops display the residual strain and a change in slope, which are characteristic of cyclic plasticity, while the fiber 0, that is the black represented by the black curve. On the opposite side, experiences large compressive strains. Its hysteresis loop indicated localized buckling under repeated compression. Both fiber exhibit strains values that reaches almost 0.04, confirming that they undergo significant plastic deformation. In addition to the stress strain behavior, we also monitored the buckling indicator, which measures the out-of-plane lateral displacement of each steel fiber, in this case, fiber 0 and fiber 9. As shown in the plot, fiber 0 shows a progressive increase in buckling indicator values after each compressive excursion, highlighting the onset and amplification of the bar buckling. Conversely, fiber 9 mostly in tension, maintaining negligible the buckling indicator values throughout the loading cycle, as we expect, because by comparing the stress strain curve and the buckling indicator time history, a clear correlation emerged. The growth of the buckling indicator for the fiber 0, here, the black line, coincides with increased compressive strain and cyclic degradation, supporting the interpretation of local instability. Moreover, the amplitude of the response difference between the two fibers. This is because we applied a loading path that I show you here, that is not symmetric at all with respect to tension and compression, and it is biased toward the compression, leading to more severe inelastic demands on the compressive side. And so as a result, fiber 0 undergoes larger deformation and instability compared to fiber 9. Despite, as you can again see here, despite their symmetric position in the section. So to conclude very rapidly, the ASDSteel1D is an uniaxial material model that brings together a wide range of physical mechanisms relevant to the nonlinear behavior of steel reinforcement, including plasticity, tensile fracture, buckling, and bond slip. What sets it apart is not only the completeness of the formulation, but also the way these phenomena are integrated in a consistent and efficient way. In short, ASDSteel1D offers a good balance between physical realism, numerical robustness, and practical usability. So thanks for your attention, and I'd be happy to take any question or comment you may have.
Thank you, Alessia. I think I already answered a lot of questions. The chat has been quite active. But anyway, and there was another interesting question, because I think we have another 5 minutes, and let me find it. There was another question. Oh, by Joel Rosas, that is asking for a comparison between this one and another nonlinear steel material. Now the point is that there is no good steel material in OpenSees for buckling. Maybe you can use some hysteretic models to calibrate the buckling, but maybe we can do a simple test using the STKO. So if you want now, Alessia, I will guide you through how to set up the STKO, but you need to create a copy of that file. So I will show people how to change to STKO, but you will not be able to see buckling in that case. So if you share a screen, Alessia, I will give you the parameters.
For sure. Okay. A moment that I share the screen. Okay.
Yes, save the file with another name just to for the user.
Okay. This is the.
Yeah, just let me take note of this is 400, 520, and 210. Yeah, I just need to take note about these numbers because I will give you. So let me see, 210 and 400 and 520 at 0.06. Okay. So for example, if you now change from, you take the standard uniaxial steel reinforcing steel materials and you go for STKO.
Okay.
Okay, in STKO, you can choose the Fy to be 400, which is the yield strength. Then you have R0, those are some default parameters. You can choose like 18, 18, and then you can choose for CR1 0.925 and 0.15 for R2. And let me calculate the hardening strength. So in your model, you need to have 220 at 0.06. So let me do a quick calculation. Divided by approximately, because I'm not interested in getting the exact one. It should be about 2000 divided by 200. Should be about 0.01. And E0 should be, well, the young modules. So 200, yeah, exactly. Okay. Now just do a quick cyclic symmetric linear increasing test. I just want to double check that everything is correctly set. Yes. Few more divisions. Do a test. Okay, that's fine. Press OK. Okay, you can press OK now.
Okay.
And but no, yeah, no, I mean it's
you have okay.
yeah, the other one. I mean in the global model.
Sorry.
So we show people what would be
Okay,
the behavior of a standard steel material without
yeah.
buckling. So save it with another name, otherwise.
Yeah, it's another.
Okay, perfect. So you can just change the steel. Perfect.
Yeah. Steel 02. We
So
said
400.
100.
Then 18.
18.
18,
Okay.
yes. Then 0.925,
Okay.
0.15, and 0.01, 210 E3. Okay, and that's it.
Okay.
And you can simply run the analysis and, well, be prepared that now maybe it will take some more iteration because now this model does not have the implex. And let's see the behavior intention. Okay, this is the initial behavior intention. As I said, if you want to lower it, this first part is governed by the tensile strength of concrete. So you can reduce the tensile strength and see if you get a better match. Okay, now we can wait a couple of minutes. As you can see now in this area, you will never see now the unloading and reloading and recovery of buckling because of course this model doesn't have buckling. Another thing that you will see is that now the unloading branch goes down the zero stress because also because there is no buckling for the same reason. Okay, but anyway, as you can see here, you will never be able to get the buckling on this model in this case. It takes a little bit longer. Now we are at half of the analysis. We are about 2.3 minutes because this one doesn't have the implex model. So as you can see, requires more iteration to converge, but in any case, it's stable anyway. So yes, it has different advantages. And by the way, in this webinar, in this example, Alessia showed only the buckling, but you can activate other features. So you can add the bond slip, you can have the fracture, or if you don't want any of them, you just want to take advantage of the robustness of the implex, you can simply use the ASD1D and switch off all the feature and it will behave as the STKO2, of course, with a different cyclic behavior, but you can get the advantage of the convergence part. Okay, so if there are no other questions, thank you everyone for taking part of this webinar. Thank you, Alessia. And as I said at the beginning, this code is now available in the official OpenSees repository. Now, as of today, you can find it in the pull request. And in the next days, I think the maintainers will include the code inside the official repository. And by Monday, you will be able to download the new version of STKO, version 4.1, that will have the user interface for the ASDSteel1D. And so you will be able to run the example that Alessia will share on Monday on our website. And also Professor Talke will compile an unofficial version of OpenSees, which already contains this new material model. So on Monday, you will be able to get everything. Okay? So thank you everyone once again, and thank you, Alessia.
Thank you so much.
There is just another question.
Okay.
Will the recording of the session be shared afterward? I really appreciate. Yes. As I said, the recording also will be available on Monday. So on Monday, you can go on our website. You can go under the webinar webpage, and at the end of that, you will find a link to the YouTube video with the recording. You will have a link to the file that Alessia will share. You will be able to download the new version of STKO and the new version of OpenSees. So you just have to wait until Monday. Okay. So once again, thank you everyone, and see you on the next webinar. Bye.
See you. Bye.
Bye bye.